Thank you, Hannes, for that kind introduction. Thank you all for joining this afternoon. My name, as has already been said, is James Griffith. I work in ARUP's San Francisco office, and my plan for the next 20 minutes is to talk through the research that we've been doing, looking into climatic load design parameters for the United States. So I'm going to give a quick overview for those of you that aren't aware of climatic loads, talk about some of the issues that they can cause, and then discuss what guidance is out there currently for engineers and designers to design, and talk about our research into seeing how those similar philosophies can be applied in the United States. So firstly, here's a cutaway of an insulated glass unit, and I'm sure I'm speaking the obvious, but there are two plies of glass, an inner and an outer piece, and around the edge is a spacer bar which keeps those plies of glass a set distance apart. And that, together with the butyl seal, traps in a volume of gas inside this unit. And it's this volume of gas which, when it's manufactured, has a certain fixed volume, a pressure, and a temperature. But interestingly, when we move from the manufacturing site to apply this unit onto a building, that volume of gas can change. It can want to expand or contract, and this happens for a variety of reasons. One of those is temperature variations. So on a hot day with high solar radiation, that gas is going to heat up and want to expand. Equally, for colder days, the opposite is true. There are variations in atmospheric pressure that fluctuates up and down, and that causes a similar expansion. And equally, the change in altitude from the manufacturing location to the installed condition can cause this pressure deviation. And so for typical flat glass and sort of the 1-inch glass that is common in the United States, this variation in pressure causes the glass to bow out or pillow. And the consequence of that is rarely structural. It's unlikely to break the glass, but it can cause these issues, which is known as pillowing, where you can visually see a lot of these deflections, particularly with highly reflective glass units, and in an urban setting where it's reflecting quite rectilinear objects, it can really be sometimes disturbing. But there are a variety of cases where these climatic pressures can cause a lot of concern, and in other presentations today, we've heard about some of them. Examples include small spandrel panels, where the glass is much, much stiffer because of its size, so it can't flex to alleviate that pressure buildup. Equally, curved glass is much, much stiffer, and so expanding gases inside that put a lot of stress both on the glass and on the edge seal, which can cause longevity issues. And also, I've called them connected pieces of glass, where the inner and the outer sheet are bonded together somehow with a bridging material. And these are just some examples of those. So the recently completed Maggie's Centre at St Bart's Hospital, with a lot of curved glass, 61 Oxford Street, and this is a good example of connected glass, where this is the Berkeley Hotel in London, where the inner and the outer ply have been bridged by an aluminium honeycomb structure that's been bonded. And all of these effects mean that this pressure buildup, this gas expansion, can't occur, and it can cause issues. And one common issue it could be is breakage of glass. And this is from a PhD where a curved piece of glass has been broken from internal pressures. So what guidance is there? How do we design for this? Well, really, the only standard and code that defines what these variations should be is the DIN 18008, the German code. And there's been a lot of work developing this into the Eurocode as well, I must say. And the DIN defines two cases, a summer case, which is the most onerous expansion condition, and a winter case, which is the most onerous contraction condition. And for each of the three areas I've talked about, the temperature, the pressure, and the altitude, a change is defined for these conditions. And going back into the history of this is based on a lot of research by Feldmayer, and the climate that was chosen for this is particularly focused on Munich, the city of Munich in Germany. Although I must say that as designers, it's pretty common to use these values widely across Europe and in some cases around the world. And so all of these three areas get combined into an isochoric pressure, which works out as plus or minus 16 kilopascals, which is the pressure that the gas would achieve if it was completely rigidly constrained. And then as designers, there's a challenge of allowing for that flex, allowing that pressure to be relieved, and finding the equilibrium point where at ASHRAE we've been developing a lot of automated software that allows us to do this analysis across an entire building. So if that was the state of play for Germany, how do we deal with the United States? The United States is much, much bigger in many ways. It covers a huge variety of climates. That previous image is also a kind of indication of scale as well. So Germany can fit right inside of Texas. And there's a lot of... Oh, just flicking through. There we go. And so there's a huge range of very different climate conditions to Germany that we should consider. So on the top left, if you're dealing with a project in Alaska, our hypothesis at the beginning of this research was that the winter case could be quite challenging. Equally, you're dealing with buildings in Vegas or in the deserts of America, where summer conditions, the heat and the solar radiation could be a challenge. We have cities like Denver, which are at 5,000 feet elevation. So how do we deal with the altitude changes associated with those? And equally, on the bottom right, there are a lot of regions which are prone to hurricanes. So we wondered whether the effect of the barometric pressure change for these major storm events would have an impact for design. And so that was really the question that we went into at the beginning of this research. What pressure values are appropriate to design glass for in the United States? So how do we go about it? Well, ASHRAE defines distinct climate zones for the entirety of the United States. And these are categorized in two ways. Firstly is in a way which kind of roughly follows vertically up through the globe. So the very bottom are very, very hot areas. And as we move vertically up through pink, red, orange, the temperature generally cools down. Equally, another interesting thing is that there are different regions as we go across the country. So on the far west coast, as we approach the Sierra Nevada, we have a marine environment where a lot of the major cities on the west coast sit. We then have a large area which is categorized as dry, or the B region. And this is much more desert-like. Vegas, Albuquerque, New Mexico have much, much more desert, dry conditions. And then we go across the Rockies and we're into the moist A region. So they're interesting to note. Also, Alaska has its own categorization of Arctic. So we thought we'd see how that works as well. And each of these climate regions has its own representative city, and that's a city that ASHRAE designated as being representative of the entire region of that climate. And it's interesting to note that Munich it's designated 5B, and so that's roughly equivalent to Chicago on this map. So what do? We took a set of weather data for every single one of these cities, which is a TMY file, or a typical meteorological year. And so we took those and Munich's, and our vision throughout this process was to try and align as closely as possible to the Munich and DIN methodology, to find the cavity temperature changes and the meteorological pressure changes. And so when we found those, we would calibrate, for instance, for the temperature changes, we would work out the values for Munich, and we found sometimes a discrepancy between what we'd calculated and what the DIN value was. And so to align those, we calibrated a certain percentile of that Munich data and applied that across the entire set of US cities. And so the results are intended to be a sort of like-for-like comparison with the DIN. And clearly further work is going to be needed to develop and align this methodology for US codes and standards. So let me show you the results. I'm going to talk about the three main components we've discussed: the temperature, the pressure, and the altitude, and then see how these merge into an isochoric pressure. So firstly, temperature. The way we consider temperature is by looking at the production conditions, and the DIN defines these as a range between plus 19 degrees and 27 degrees Celsius. And then we need to consider what the temperature is in the cavity when it's installed. And the winter condition considers purely outside and inside air temperatures. And in summer, it adds in an element of solar radiation as well, and glass absorption. And so to get the temperature change, for summer, we take the lowest production condition and the highest summer condition. And for winter, it's the opposite, so the highest production and the lowest winter value. And this is the set of results. And I'm just going to take a little bit of time to explain this, because there's a lot of information here. This is a plot of both the winter and the summer condition. So every city on here has its own point. And to accommodate both the sort of Americans amongst us and the rest of the world, I've plotted on the sort of, if you're thinking Fahrenheit and imperial units, maybe think about the left-hand side and the bottom edge of these graphs. And if you're more thinking in SI units, the top edge and the right edge are maybe the best to look at for scale. So here we've got both the summer temperature change and the winter temperature change. And so we can see Munich, highlighted in the red dot, has that is the DIN values, the plus 20 for the summer and the minus 25 for winter. And then we can start to see how these distinctive representative cities fall relative to Munich in terms of this temperature change. So highlighted sort of from the left up to that point in this region are all the cities that would fall within the DIN values for summer. And you can see that there's a large range of values which are higher than that in the States. And particularly I'm highlighting these dry B climates, which are the desert climates, which can have significantly higher temperature changes that should be considered. And equally, if we think in terms of winter, so coming down as it gets colder, up to the Munich values, there's a couple of points. The most extreme values here are from the cold and the Arctic regions. So we can expect much lower temperatures in winter in those regions that need to be considered. Another interesting point to think about is the effect of the verticality of the glazing. In Munich, which is situated at roughly 45 degrees latitude, the effect of horizontal versus vertical is actually quite limited. It's essentially the same solar angle for both the horizontal and vertical piece of glass. But we ran all the analysis for both horizontal and vertical. So the results previously were for vertical glass, which is more common. And this is a plot for horizontal glass. So it's worth noting that there can be, this is quite an increase or decrease in the temperature, depending on its orientation and its latitude. So on the higher latitude areas, lower latitudes over here, there's quite an increase because of that effect. And on the higher latitudes, there's a decrease. Next up is pressure. The way that we understand the DIN to define pressure variations is considering a range of values, a minimum value, a maximum value, and a mean value for both production and installed conditions. And so the sum of pressure variation is taken as a difference between a mean and maximum, and the winter as a maximum to a minimum. And this is the plot of all those data, all those pieces of data for barometric pressure changes. So in summer conditions, all of them pretty much fall within the Munich data. But when we look at winter, there is some variation. This selection up here all fall slightly outside of that, and it's roughly a 1 kilopascal increase in those winter conditions. And finally, let's discuss altitude. To consider the altitude, we need to think of where the insulated glass unit is assembled, where that pressure is locked in at assembly, and then consider where it's being installed. And that change in height from production to installation needs to be considered. And we at ARAP have a database of manufacturers, IGU assemblers, and so we plotted the altitude of every single one of those in North America. And this is the scatter we get. So a large number, the 90th percentile, is below 400 meters altitude. And there are a few outliers which I've outlined. So, as discussed, Denver is a very high altitude. Salt Lake City, again, very high altitude. So for this, we took the 90th and the 5th percentile as a set of values which capture the majority of glass processes. And then for every representative city, we worked out the possible altitude changes that you could expect if the glass was manufactured there. And again, if we consider this is for a winter change, the Munich value seems to be pretty representative of that. There are some extensions below. But it's the vertical variation, the summer variation, which is very high. And it's these dry climate regions, the B regions, because of their high altitude, which cause this. And interestingly, there is some guidance on altitude variation defined by the Insulated Glazing Manufacturers Alliance and the Glass Association of North America, Ghana, which define a 2,000 and a 2,500 feet marker above which you should start thinking about pressure equalizing your units. So it was interesting to see how those lines align quite interestingly with the data here. And so finally, how does all that combine together? Because it would seem unreasonable to sort of take envelopes at each case and just keep combining the worst cases. You can end up with some quite high stacks of load. So for each city, we took the temperature, pressure, and altitude and worked out what the isochoric pressure would be. So the Munich data is that DIN value of plus or minus 16 kPa for winter and summer. And this is the scatter that we see. So for summer conditions, a large number of cities fall within those, and particularly it's the dry climates where very high pressures, in some cases up to double the pressure of DIN, were found using this method. And for winter, there, again, with a slightly expanded envelope, you could imagine capturing all of those values. And perhaps unsurprisingly, the Arctic value, Fairbanks, Alaska, falls about 5 kPa further beyond those DIN values. So let me conclude. There's been a lot of graphs. What are the conclusions? So when we use this method of trying as much as possible to align with the DIN methodology and calibrating the data to that, we found that for most of the moist and the marine climate zones, those ones nearer the coast, an expanded set of DIN values which include an additional couple of kilopascals could capture the majority of those cases. But the dry climates seem to need special consideration because of those extra high temperatures and altitudes that are present. Equally, Arctic climates might need extra special consideration because of the low temperatures. But I hope this is the beginning of a conversation around this topic, and I think there's a lot of further work that, as both industry and academia and as designers, we need to think about before we can develop guidance for the United States. I think there needs to be a more clear statistical basis and established methodology for working out these changes and which values to take for each. I think the appropriate recurrence intervals for the climate data need to be considered. What weather data should we use? We used TMY data in this case. And also, a lot more work needs to be done to think about how to align these calculations with the existing calculations defined by the US codes and standards. So it's worth giving a quick thanks to the research team that was involved. It was a wide research team within the San Francisco office with Felix Weber, Sophie Moore, Ingrid Chiares, and Alexei Goering. And thank you for listening. I'm sure there are plenty of questions that result from this, and I'd be happy to field some.
Thank you, James. Interesting piece of work. Any questions from the floor? Is the mic around? In the middle. There you go.
Cheers for the presentation. I've got 2 questions. The first one is, have you considered transport routes? If, for example, your mode of transport is by truck and you're passing over mountain ranges from a production site to an installation site, is that something that you would integrate into this analysis?
Yeah, so for this research, we didn't. We just considered the locations of the production and the installation. But quite feasibly, when you're sort of plotting those routes, it would be very sensible to include that. And it's interesting that we've tended to observe that there's not a huge amount of transit between, or sort of over the Rocky Mountains. There's this kind of dividing line in America where glass tends to be sourced and installed from one side and not done, it's sort of done separately. But I think certainly there should be definite consideration of that in the analysis. Yeah.
Okay. The second one is, how do you plan on applying this information once you've got results? Because I imagine there's sort of 2 sides of it. One would be maybe strength, where you're looking at sizing your silicon joints for the climate load that you end up with. And the other would be, I guess, more of a service condition where you could potentially, if you've got positive and negative isochoric loads and they're quite high,
sure,
you have a kissing condition or a pillowing condition like you talked about. How would you design for that? A pressure equalization, or how do you find a value that you design for?
Sure. So I guess the scope of this research was really focused on trying to look at those isochoric pressures. In this study, we didn't do much beyond in terms of the design, applying those, and how to mitigate them. But there are quite a few options out there to mitigate those pressures. So, yeah, as you say, pressure equalization, having breather tubes, permanent breather systems that breathe through desiccant chambers are all possible. Equally, you mentioned the transportation. There are examples where the glass is transported in a refrigerated unit to try and eliminate those challenges of going over different altitudes. So, as I say, for this research, we haven't really studied that, but I feel like there's a pretty well-established body of research looking into that. I would say for the sort of serviceability cases, a lot of that is a kind of quality issue for the flat glass, and so there are values which we can think about defining and ways of building up the glass to reduce the visual impact of those reflections.
Any further questions before we move on? One at the back there.
Thank you very much for this interesting work. Just a short remark from my side. You worked with the standard temperature values of plus 20 degrees centigrade, for example. In the code, or in the annex of the code, there is the boundary condition named, which is special radiation, special absorption, everything. And there is another table which you have to look at if you have different glass setup. So a higher absorption, for example, you have to take another 9 Kelvin plus temperature, for example. And this additional temperature you have to look at goes up to plus 18 centigrade. Because, of course, since Feldmayer did his studies, IGUs developed. And at the actual situation, if you do a design in Germany for a state-of-the-art IGU, you no longer calculate just with the 20. Usually you have the plus 29 degrees centigrade. I'm not sure about the state-of-the-art of IGUs in the US, maybe.
Sure. So, yeah, we're very aware of the table and those additional sort of add-ons, you could say, to boost up the temperature values. For this, we didn't look into that. It would have sort of, I forget how many lines there are on that table, maybe 8. So it would have multiplied by 8 the amount of research we would have needed to do. So we didn't look into that, but I think certainly as this work develops and this research in the US develops, I think certainly it would need consideration. Yep. We purely use the values in the annex to define those boundary conditions.
Okay, no more questions. Thank you, James. Very informative and much more to do and bring next time. Thanks.
Sure.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao!